Hello, everybody. This is our Zoom meeting, problem solving for chapter 2. Once again, I will be going through all the examples in chapter 2. I urge you all to go through this recording, solve the problems, solve them once, twice, 3, 4 times, however many times it takes you to get a deep and profound understanding of the problem. Every single time you solve it, you'll get a little bit more insight into the subtleties of physics, and you cannot solve a physics problem too many times, in my opinion. Okay, this is example 2.1. It is average and instantaneous velocities. And it reads, a cheetah is crouched 20 meters to the east of a vehicle. At time t equals 0, the cheetah begins to run due east toward an antelope that is 50 meters east of the vehicle. During the first 2 seconds of the chase, the cheetah's x-coordinate varies with time according to the equation x equals 20 meters plus 5.0 meters per second squared times t squared. A, find the cheetah's displacement between t1 equals 1 second and t2 equals 2 seconds. That's our challenge for A. And B says finds the instantaneous velocity at t1 equals 1 second. So B says instantaneous velocity at t1 equals 1 second. Let's see. By taking delta t is 1 second, and then 0, 0, 1 second, and 0, 0, 0, 1 second. I guess before and after. Okay. Oh, wait a minute. That was C. I'm sorry. Find the average velocity during this time interval is B. Okay. So A was find the cheetah's displacement between 1 second and 2 seconds, and B was find the average velocity. Now C, I'm sorry, this is C. C says find the instantaneous velocity at t1 equals 1 second by taking delta t is 0.1 seconds, and then delta t of 0.01 seconds, and then delta t of 0.001 seconds. So we have 3 delta t's. Delta t1 equals 0.1 second. Delta t2 equals 0.01 second, and delta t3 equals 0.001 second. So we'll take the limit there. Let's see, and derive an expression for the cheetah's instantaneous velocity as a function of time. So we need a d, we need to find dv dt. We need to find an expression for that. And use it to find v sub x, and then we need to find it for the velocity v sub x at t equals 1 second, and t equals 2 seconds. So we have an expression for the displacement. We're asked to find displacement at these 2 times. We're asked to find the average velocity between those 2 time intervals. Then we need to find the instantaneous velocity at 1 second by taking smaller and smaller incremental limits. And finally, we need to find an expression for the instantaneous velocity. And with that expression, we need to solve for that velocity at 1 second and at 2 seconds. All right. A. Okay. At t equals 1.0 seconds and t equals 2.0 seconds, we will find the cheetah's position. So x of t equals 1 second is going to be 20 meters plus 5.0 meters per second squared times 1.0 seconds quantity squared, and that's going to be equal to 25 meters. All right, x at t equals 2.0 seconds is going to be 20 meters plus 5.0 meters per second squared times 2.0 seconds quantity squared. That will give us 40 meters. Okay, so the displacement during the first time interval is delta x is going to be equal to 40 meters minus 25 meters. That's going to be equal to 15 meters. For the average velocity, we'll simply v average is going to equal delta x divided by delta t. This is going to be equal to, as we saw, 15 meters. And then we have 2.0 seconds minus 1.0 second, and we'll get 15 meters over 1 second, or 15 meters per second. Note the units of velocity are meters per second here. That would be the average velocity between those time intervals. All right, for C, we want to know the velocity at delta t equals 1.0 seconds, and we're going to take an interval from of 0.1 second. So our delta t1 is going to be 1.0 second, and delta t2 is going to be 1.1 second. So let's go ahead and do this. We let's see. We know that delta t at 1 second is, we already solved that, 25 meters. So delta x, I'm sorry, delta x equals 25 meters for this time. And now to solve for the next, we're going to get x at t2 equals 20 meters plus 5.0 meters per second squared times 1.1 second quantity squared. And our answer is going to be 26.05 meters. So delta x here, we'll call this delta x2, and that delta x1 is going to be 26.05 meters. All right, so our V average equals 26.05 minus 25 meters. This is delta x, and that would delta t would be 1.1 second minus 1.0 second. This will give us 1.05 meters divided by 0.1 second, and that's going to be 10.5 meters per second. 10.5 meters per second. And you should do the same procedure for the intervals of 0.001 second and 0.0001 second. Same procedure. And you will find that you get greater and greater accuracy. Okay? you get closer to 10 meters per second as your limit gets smaller and smaller. Or number D, we are asked to find the instantaneous velocity of v sub x. We're looking for dx dt, instant. So we will take the derivative of, let's see, v sub x equals d of 20 meters plus 5 meters per second squared times t squared. And that will be dt. So we're going to get, taking the derivative of 20 meters with respect to t is 0. And this is going to be 10 meters per second, 10 meters per second squared times t, 10 meters per second squared times t. And this will give us at, okay, so that's our, let me just erase it. So I'll move our equation up here. We're going to get 10 meters per second squared times t. And we're looking for the value at t equals, what, let's see, t equals 1 and 2. Okay, so at t equals 1, we're at v sub x at t equals 1.0 seconds. We'll get 10 meters per second squared times 1 second. That's going to give us 10 meters per second, exactly what we found in part C. And then at 2, let's see, 10 v sub x at t equals 2.0 seconds is going to equal to 10 meters per second squared times 2 seconds, and we will get 20 meters per second. Example 2.2 is one that explores average acceleration. And it goes, an astronaut has left an orbiting spacecraft to test a new personal maneuvering unit. As she moves along a straight line, her partner on the spacecraft measures her velocity every 2.0 seconds, starting at time t equals 1.0 seconds. And so now we have 8 measurements of her velocity at 8 different times. So we have 1.0, 3.0, 5.0, 7.0. It looks as though we are skipping 2 seconds every measurement. Now our mission is to find the average x acceleration and state whether the speed of the astronaut increases or decreases over each of these 2 second time intervals. So our first one is A, from t equals 1 second to t equals 3 seconds. T 1 equals 1 second, and t2 equals 3 seconds, 0.0 seconds. Our second interval is t1, B would be t1 equals 5 seconds, and t2 equals 7 seconds. C is going to be t1 equals 9, and t2 equals 11 seconds. Finally, D, t1 equals 13 seconds, 13.0. This is 9.0 seconds, I stand corrected. And oops. All right. And finally, right here, t2 equals 15.0 seconds. All right, so we are going to once again find the average acceleration and state whether the speed of the astronaut increases or decreases over these 2.0 second time intervals. All right, in order to solve for the A average, we're going to take V2 minus V1 over T2 minus T1. So acceleration average is delta V over delta T, which would be the final velocity minus the initial velocity divided by the final time minus the initial time. So for our first interval, we have, let's see, 1.2 meters per second, 1.2 meters per second minus 0.8 meters per second divided by, we know this is a 2-second interval, right? Yes, it's three, all of them are 2-second intervals. So I will just put, well, I'll do it correctly. 3.0 seconds minus 1.0 seconds. So here we will get a, let's see, 0.2 meters per second squared, 0.2 meters per second squared. And note the units here. Acceleration has units of meters per second squared. So in this case, we are increasing. Okay, our speed is increasing. Our speed is increasing if the sign of our velocity and the sign of our acceleration are the same sign, not S-I-N, but S-I-G-N. So we are, in this case, we are increasing in the positive direction. Part B, our second interval. We want to know, let's see, the speed from, let's see, what B, the speed from, let's see, where was it? 1 second. Part B, we are going to use these two intervals. All right, so our final is 1.2 meters per second minus 1.6 meters per second divided by 7.0 seconds minus 5 seconds. And here we will get a negative 0.2 meters per second squared. Once again, take a note of the units. It's very important to get your units right in physics. Acceleration has units of meters per second squared. Now you'll note that we have a negative acceleration here with a positive velocity. So in this case, our speed is decreasing. When we have different signs, we are decreasing. We are traveling in the positive direction, and we have an acceleration that points towards the negative direction. So we are decreasing now. Okay, for our third interval, we are using these two values. So we have our final would be a negative 1.0 meters per second minus a negative 0.4 meters per second. And once again, we have 11 seconds. We know it's 2-second intervals here, but we'll just be more nearly correct and do everything proper, because sometimes it's not that easy and it's good to get into good habits. 9.0 seconds. And our value here is going to be a negative 0.3 meters per second squared. Once again, I can't be too insistent upon making sure you are familiar with the units for every value or every term that you need to express. And for acceleration, it's going to be meters per second squared. And so we are having a negative velocity and a negative acceleration. Our speed is increasing in this case in the negative direction. So our signs, this negative and these negatives, we are having an increase in the negative direction. All right, finally for D, we are examining, oops, let me get my pencil out. We are finally examining these final two interval, this final interval here between these two values, or these two sets of values. And so what we have is we're going to do a negative 0.8 meters per second. That's our final velocity, minus our initial, which would be a negative 1.6 meters per second, divided by 15.0 seconds minus 13.0 seconds. And our value here is going to be a 0.4 meters per second squared. Our acceleration average acceleration between this interval is 0.4 meters per second squared. In this case, we have a negative velocity and a positive acceleration. We are traveling in the negative direction. However, we have our acceleration going towards the other direction. We are slowing down, yet traveling in the negative direction. Example 2.3. Our topic is average and instantaneous accelerations. And the problem reads, suppose the x velocity, v sub x, of the car in figure 211, it's a car in your book, a cartoon of a car, at any time t is given by the equation v sub x equals 60 meters per second plus 50 meters per second cubed times t squared. All right, we need to find the change in the x velocity of the car at the time interval t equals 1 equals 1.0 seconds to t2 equals 3.0 seconds. This is t1, t2 equals 3.0 seconds. Find the change in the x velocity of the car. So we need to find the change. And B, we are asked to find the instantaneous x acceleration at t1 equals 1 second by taking delta t to be the first 1 second and then to be the 0.01 second. And then, okay, so we are going to do the same thing we did in the velocity example. So, oh wait, I'm sorry. B said find the average acceleration in this time interval. So now we have to find A average in the above interval. All right, C asked us to find instantaneous acceleration at time t equals 1 by taking the limit of smaller and smaller increments. So we find t equals 1 by taking delta t to be first equal to 0.1 second, finally 0.01 second, and 0.001 second. And then finally, derive an expression for the instantaneous acceleration as a function of time. So we need to find, for that, we need to find dv dt. We want to find A. We want to get that expression. And then we want to find A sub x at t equals 1 second, 1.0, and t equals 3.0 seconds. Okay, so that's our mission. Okay, so question A. Find the change in the x velocity of the car in the time interval during t1 to t2. Okay, so we know that we will find v sub x at t1 equals 60 meters per second plus 50 meters per second cubed times 1, is that 1 second? 1.0 seconds squared. And that's going to be 60. Oh, this is 0.5. I'm sorry. This is 0.5. 0.5. This is 60.5 meters per second. Meters per second. This is second squared times second cubed will give you a meters per second. And V sub x at t equals 3 seconds, 3.0 seconds. We are going to get 60 meters per second plus 0.5 meters per second cubed times 3.0 seconds, quantity squared, will give us 64.5 meters per second. Right. All right, now we need to find the change in velocity. So we're going just to take the difference here. So delta V equals V final minus V initial, which would be 64.5 meters per second minus 60.5 meters per second. And that's going to give us equals 4.0 meters per second. So that's delta V. This is the answer to A. B asks us to find the average acceleration during that time interval. So A, average, is going to be equal to delta V over delta T. So we already know delta V is 4.0 meters per second. And our time interval was from final was 3.0 seconds minus 1.0 seconds. So this is going to be 4.0 meters per second divided by 2 seconds. Our answer is going to be 2.0 meters per second squared. Once again, there's that meters per second squared unit again, that unit of acceleration. For C, where we want to find this average acceleration at t equals 1 second. 1.0 second. And we want to do this by basically taking the limit as delta t gets smaller and smaller. I'll do the first one for you, and I hope that you do the other ones on your own. So my time increment here is going to be delta t equals 0.1 second. So, okay, so I need to find, I know my V1 at 1 second. My V at t equals 1 second from the part A was going to be 60.5 meters per second. Now I want to know what V at t equals 1.1 second is. So I'm going to do that. And let's see, we've got our equation 60 meters per second plus 0.5 meters per second cubed times 0.1 second quantity squared. That's going to give me 60.605 meters per second. 60.605 meters per second. And let's see, now to find my average acceleration, I'm going to A average, once again, equals delta V over delta T. And delta V is V final minus V initial. Delta T is T final minus T initial. So we've got 60.605 meters per second minus 60.5 meters per second divided by 1.1 seconds minus 0.1. I'm sorry, 1.0 seconds. And my answer there is going to be, I'll put my answer to this down here. A average is going to equal 1.05 meter per second squared. And I'll let you do the rest, and you can see what the limit approaches as the time increment gets smaller and smaller and smaller. All right, finally, part D asks us to find an expression for the instantaneous acceleration. Okay, so we have our expression V sub x, and we want to find A, and we know that A equals dv dt. which equals d, 60 meters per second, plus 0.50 meters per second cubed, times t squared, that's dv, dt. Okay, so we're going to get, let's see, that's going to equal to 0.5 meters per second cubed, that's the constant, times 2t, which is going to be equal to 1.0 meters per second cubed times t. And I need to solve for this at t equals 1 and at t equals 3. So let's go ahead and do that. Once again, my expression for my acceleration at any given time t is 1.0 meters per second cubed times t. So when t equals 1, a equals 1.0 meters per second cubed times 1, and that's just equal 1 second, I'm sorry. That's going to equal to 1.0 meters per second squared. And you see our units do work out, and that is one way to check your answer in physics. And at p equals 3 seconds, a equals 1.0 meter per second cubed times 3 seconds. And this is going to be equal to 3.0 meters per second squared. So these are our instantaneous accelerations at time t equals 1 second and at time t equals 3 seconds. And this is our expression. This is example 2.4, and we're going to be calculating some values given a problem that has constant acceleration. So our problem states that a motorcyclist heading east through a small town accelerates at a constant acceleration of 4 meters per second squared. So I'm going to write down what we know. We know our acceleration is 4.0 meters per second squared. We know that his direction is east. I don't know if that's going to be germane to the problem, but we'll write that down anyway. And after he leaves the city limits, at time t equals 0, he is 5 meters east of the city limit post. So x at t equals 0, and we'll call the city limit signpost 0, so equals 5 meters. Let's see, at time he is of the city limit signpost while he moves east at 15 meters per second. So v at t equals 0 equals 15 meters per second. So this is what we know. We know his acceleration is constant. It's 4 meters per second squared. We know his position at time t equals 0 is 5 meters. And we also know his velocity at time t equals 0 is 5 meters. All right, now, let's see. We are asked to find his position and velocity at t equals 2 seconds. So we need to know his position and velocity at t equals 2 seconds. And where is he when his speed is 25 meters per second? All right, so find his position and velocity at t equals 2 seconds. So for A, we want to find x and v at t equals 2.0 seconds, right? 2.0 seconds, that's correct. All right, so we're going to use our kinematic expressions that we talked about in the instructional videos. We'll use our displacement expression, which says x final, this is to find x, equals x initial plus v naught t plus 1/2 at squared. And this expression v naught here, I'm in the habit of using that. That it just means initial, this little naught. So these things are interchangeable. I just got in the habit of using that, so I just wanted you guys to know that. So x final is the value we're solving for. So x final equals his initial position at t equals 0 is 5 meters. His initial plus 15 meters per second, that's his initial velocity, times 2.0 seconds plus 1/2, and his acceleration is 4.0 meters per second squared. And at the time again is 2.0 seconds, and this is going to be quantity squared. And if you do the math on that, you'll find out that x is going to x at t equals 2 seconds. This is x final, I'm sorry. That t equals 2 seconds is going to be 43 meters. You do the math on all this. Once again, when you do the math, don't forget your little operations here. You want to square both the 2.0 second and the seconds here. That's inside the parentheses. So, all right, so that's your position. Let me erase this. Now we need to find our velocity in 2.0 seconds. For that, we're going to use the velocity equation, and this is still part A, right? Okay, so our velocity final, VF, is going to equal to the velocity initial plus acceleration times time. So our final velocity is going to be equal to velocity initial is 15 meters per second, plus our acceleration is 4.0 meters per second squared, and our time would be 2 seconds. And doing the math on that gives us 23 meters per second. VF equals 23 meters per second. And note, this is an expression for velocity, so its units are meters per second. All right, for challenge B, we want to know where is he when his speed is 25 meters per second. For this, we'll use the no time equation, all right? So we have V final squared equals V initial squared plus 2A delta x, and we are solving for delta x. So we know that we want to find V final is going to be 25 meters per second. This is going to be squared equals 15 meters per second, also squared, plus 2 times 4.0 meters per second squared times delta x. Solving for delta x, we have 25 meters per second. Quantity squared minus 15 meters per second. Quantity squared. And then that's going to, I'll divide by 2 times 4 meters per second squared. That's going to give me delta x, and we'll find that delta x is 55 meters. Example 2.5 is called two bodies with different accelerations. This is a problem that I've seen in many, many physics books. So this seems to be a problem that they like to put in these books. Anyway, it goes like a motorist traveling at a constant 15 meters per second, about 34 miles an hour, passes a school crossing where the speed limit is 10 meters per second. So what we want to know is the motorist. We'll put down his motorist. He's got a velocity that's 15 meters per second. And I believe this whole speed limit thing being 10 meters per second is just to show you that he's breaking the law and going too fast. Okay, I don't think it's just as the motorist passes the school crossing sign, a police officer on a motorcycle stops there, starts in pursuit with constant acceleration of 3 meters per second. So now the policeman has a acceleration of 3 meters per second squared. How much time elapses before the officer passes? At that time, what is the officer's speed, and how far is each vehicle traveling? Okay, so just as a motorist passes the school crossing sign, a police officer on a motorcycle stopped there. Okay, so there's no lag time. So the police's initial velocity starts from rest. So he's got a initial velocity of 0 meters per second. All right, so A, how much time elapses before the officer passes the motorist? Elapses before the officer catches up to the motorist. And then B, what is the officer's speed and how far is each vehicle traveled? So B, officer speed. And C asks us for delta X of each vehicle, which I assume they're going to be the same since they start from the same location and they'll catch up with each other at the same location. All right. All right, for the first challenge for A, we want to know when they will be at the same position. So what we need to do is we need to find, set up this equality, X of the motorist equals X of the police officer. So let's see, for the motorist, we have X final. We'll call our initial position equal 0. So that's going to be 0 equals V naught T. Oh, remember, we're using our displacement equation. I'll write that down. X final equals X initial plus V naught T plus 1/2 AT squared. So X final equals 0. We're calling this 0 for both of them. For the motorist, it's 15 meters per second times T. And the motorist is not accelerating. He's not trying to get away from the officer. So this is an expression for his final position. And for the police, X of the police officer, we have, again, 0. X final is X of the police officer, 0. And he has no initial velocity. So that term is 0 too. So it's going to simply equal to 1/2. A is 3 meters per second squared, and then times T squared. So if the police officer is going to catch the motorist, well, just X final less of motorist, when their positions are the same. So if I set these two values equal and I solve for T, I'll be able to find out when he will catch. So I have when the police officer will catch the motorist. So 15 meters per second times T equals 1/2 times 3 meters per second squared times T squared. All right, it's a simple matter to solve for T. I can just take a T out here and a T out there, and I get, let me clear all this up. Okay, working with this expression here, I have, I'm going to multiply both sides by 2, and I'll get 30 meters per second equals 3 meters per second squared times T. I'll divide both sides by 3 meters per second squared, and I'll get 30 meters per second divided by 3 meters per second squared equals T, and T will be equal to 10 seconds, equals 10 seconds. Challenge B asks us to, let's see, what was B asking? We want to find, let's see. Okay. B, find the magnitude of the officer's X velocity at the time T that we found in part A. So we know that T equals 10 seconds. So the officer, okay, so we have our velocity expression, V final equals V initial plus acceleration times time. So we want V final. So V final, he has a 0 initial velocity plus, that was 3 meters per second squared times 10 seconds. So our V final is going to be equal to 30 meters per second. The officer's final velocity is 30 meters per second. Finally, we're asked to solve for how far away from this initial point were they when they finally met up. So we know that they're both in the same spot, final spot. So I could use either expression and use my time t equals t 10 seconds and solve for this. So let's take the motors. So x final equals x initial plus v naught t plus 1/2 at squared. Okay, so I'm solving for x final. I know my initial position is 0, and my initial velocity is 15 meters per second. My time is going to be equal to 10 seconds from part A, and the motor has no acceleration. So my final position is going to be 150 meters. It will be the same for the officer, but we can solve it that way just to prove it. X final of the officer equals, once again, that's 0. The initial position is 0. His initial velocity is 0. We have 1/2, and he's got 3 meters per second squared times 10 seconds, quantity squared. And this will also give us 150 meters. Example 2.6 is an example that shows us how to solve situations when we have an object in free fall. So it's called a free falling coin. A one-time euro coin is dropped from the Leaning Tower of Pisa. If you haven't been there, you got to go there. And falls freely from rest. What are its position and velocity after 1 second, 2 seconds, and 3 seconds? Okay, so we want to know position and we want to know velocity. So for this, we will use our position equation and we'll use our velocity equation. So recall once again that our position equation, and let me interject here and suggest very strongly to you guys that it would be a great idea for you to memorize your kinematic equations. You have a whole video, instructional video on those in under your chapter 2 instructional videos. And obviously for the test, I'll give you all the equations, but you will probably do best on the test and be more successful if you all have used these so much that you commit them to memory. So I do strongly suggest that you memorize these equations. Anyway, I digress. So here we go with our displacement equation. X final equals X initial plus V naught T plus 1/2 AT squared. This is our displacement or our position equation. And our velocity equation is V final equals V initial plus acceleration times time. Okay, and perhaps you can see that this guy is a derivative of that guy. Can make the time derivative of it. Take a few minutes to take the derivative of the position function and you'll see that you actually get the velocity function. Anyway, I digress again. So what are we solving for? We're solving for the position and velocity after 1 second, 2 seconds, and 3 seconds. All right. So let's see. We have a position. So x at t equals 1 second, and v at t equals 1 second. So I'm going to do one of these for you. I'm going to do the 1 second one for you, and I'm going to leave it to your pleasure to solve for the 2 seconds and the 3 seconds in the same manner as I do this. All right, so x at 1 second. So x final, this is what we are looking for. And we're going to ignore air resistance. So we can solve these. It makes it easier to solve. I'm going to call that initial position 0, right? Let's see. What's its position and velocity after 1 second, 2 seconds, and 3 seconds? So we'll call the top 0, and we'll call that downward direction positive, if you will. Okay, so we have 0 plus, it's dropped from rest, so that term is also 0, plus 1/2, and our acceleration in this case is due to gravity. 9.8 meters per second squared, times 1 second, and this quantity is squared. So let's see, that's going to be what, 4.9 meters, right? Yes. So this is going to be equal to 4.9 meters. Now for our velocity in 1 second. So VF equals our initial velocity. Once again, it's dropped from rest. So we have a 0 initial velocity, 0 plus AT. This is that. So plus 9.8 meters per second squared times 1 second. So our final velocity is going to be 9.8 meters per second. And that's a 9. And so I'll leave it to your pleasure and to your practice, and I highly suggest you practice, to solve for the, it wants to know where the 2 seconds and the 3 seconds. So solve for position and velocity at t equals 2 and t equals 3. It'll give you some wonderful practice. Okay, example 2.7 is an up and down motion in free fall. So what's going to happen is we're going to toss something up and we're going to evaluate its motion. Obviously, it's going to go up. It's going to reach a certain height depending upon the energy with which we toss it, and it will come back down due to gravity. So here we go. You throw a ball vertically upward from the roof of a tall building. The ball leaves your hand at a point even with the roof's railing, with an upward speed of 15 meters per second. So we're going to call this, we'll call that upward speed positive. So V equals 15 meters per second. So if our upward speed is positive and our acceleration will have to be negative because it will be slowing it down. So we'll go ahead and write that down. A is going to be equal to negative 9.8 meters per second squared. Obviously, I could have called that upward direction negative, and I could have called this, then my acceleration would have been positive, but it's, first of all, it's customary to use gravity as a negative in the downward direction. But it doesn't matter as long as you're consistent. Okay, anyway. On its way back down, it just misses the railing. So that implies that it just goes straight up and straight down. Find the ball's position and velocity at 1 second and at 4 seconds after leaving your hand. Find the ball's velocity when it is 5 meters above the railing and the maximum height reached. The ball's acceleration when is at its maximum height. Okay, so how tall is the building? Is it a tall building? It doesn't say, but what we'll do is we'll use the height of the building as our 0th point. Okay, I guess that's what we'll do. It doesn't say how tall the building is, like this big. All right. Okay, so let's see. We're supposed to find the ball's position and velocity at 1 second and at 4 seconds. Okay, so we need x at t equals 1 and at t equals 4, and v at t equals 1 and t equals 4. All right, so once again, we'll use our kinematic expressions. We'll use the displacement, x final equals x initial plus v naught t plus 1/2 at squared. And for our velocity, we'll use v final equals v initial plus acceleration times time. All right, for x final, since we're calling this 0, our ball is going to go up and back down. This will be our 0th point. Anything above this is going to be a positive position. Anything below it will be a negative. For the velocity, when the ball is going in the upward, that direction we'll call that positive, and this direction will be negative. All right, so for our position, x final, we'll start at 0 equals 0. We have an initial velocity of 15 meters per second times 1 second plus 1/2, and we've got a negative 9.8 meters per second squared times 1 second quantity squared. Let's see if the book has solved this for me or no. Gotta use my calculator. All right, what do we have here? On 50, okay, so we've got 15 meters plus clear 9.8 times 1 divided by 2 equals minus plus a negative 4.9 meters. And let's see, clear 15 minus 4.9 is going to give me 10.1 meters. 10.1 meters. So it's going to be, that's positive. So it's going to be 10.1 meters here. All right. That is the position at t = 1. Let me erase. And I'm going to go ahead and solve this for t = 4 for you because we might have a negative value. I don't know what we're going to have, but it might be a little confusing. But let's go ahead and solve this together. So for position, x at t = 4. Once again, we're calling that initial position 0. Our initial velocity is 15 meters per second times 4 seconds. I'm going to go ahead and plus a 1/2 times a negative 9.8 meters per second squared times 4 seconds, and that's quantity squared. Let me go ahead and calculate that. So clear 15 times 4 is going to equal x at t = 4. It's going to be equal to 60 meters plus it's going to be a negative clear 4 times 6, wait, clear 16 times 9.8 equals divided by 2 equals minus a 78.4 meters. So at 4 seconds, it's going to be here 78.4 meters below our 0 point. It's going to be somewhere down there. Let's see. All right, so it's going to go up, but it's going to come back down. All right, let me pause, clear off my board. Oh, I am sorry, correction. Position 2, it's not going to be 78.4. I forgot to add the 60 to it. It's going to be negative 18.4 meters. So it's going to be not here, somewhere around here. Remember, this is our 0th position. It's going to be negative 18.4. I forgot to add that 60 to the 78.4. So at x at t = 1, I forgot what that was. Let's see, that would be 15 minus 4.9. Let's see. Plus 5.2 meters per second. And the 7 equals 5.2 meters per second. And no, that's wrong. All right, it's going to be what? A 15 minus 4.9, which would be 10.1, right? Yeah, 10.1. 15 minus 4.9 is 10.1 meter. Add this x at t = 1 and x at t = 4 is going to be negative 18.4. So what's going to happen is after 4 seconds, your ball will have gone all the way up and it have already started to come back down and reach this spot here, which is 18.4 meters below its starting position. All right, so that's for our position. All right. Now I need to solve for my velocity at t = 1 second and t = 4 seconds. So my velocity V final equals V initial plus acceleration times time. So V final equals 15 meters per second plus a negative 9.8 meters per second squared times 1 second. And this is going to be what? 10.01? Wait, 10.0. No, let's see here. 15 minus 9.8 is clear. 15 minus 9.8 is going to give me 5.2 meters per second. For my velocity final, this is t equals 1 second. T equals 4 seconds. It's going to be the same procedure, 15 meters per second. And we already know it's going to be in the negative direction, right? Because we solved for that position. The ball is going down at this point. Plus a negative 9.8 meters per second squared times 4 seconds. So let's do that. 15 minus 9.8 times 4. And I get negative 24.2. Negative 24.2 meters per second. So that indicates that the ball is going the opposite direction as when it started out. It's falling towards the earth now. All right, in part B, we want to know the ball's velocity at x equals 5 meters, positive meters. Okay, so we're going to use V final squared equals V initial squared plus 2 times A times delta x, where delta x is 5 meters. So V final squared equals 15 meters per second squared plus 2 times negative 9.8 meters per second squared times 5 meters. And let's see. This is going, okay, so we've got, let me do this. Clear 15 squared, enter, plus 2 times negative 9.8 times 5. And let's see, I get V final squared equals 127 meters squared over second squared. So V final is going to equal the square root of 127 meters squared over second squared. And let me get that right now. And it's going to equal 11.2 meters per second. So that's V final. Or that's what V is at the position 5 meters per second. So you started at 0, it's going 15 meters per second. When it's gone 5 meters above your initial position, it's slowed down to 11.2 meters per second. Finally, the problem asks for the ball's acceleration at its maximum height. Well, the ball's acceleration during its entire trajectory is negative 9.8 meter per second squared. A lot of people, a common mistake, people will assume that its acceleration is 0 at its maximum height. And this is not true. Its acceleration, the acceleration of any object near the surface of Earth is always has a y component that points towards the center of Earth, and the magnitude would be negative, would be 9.8 meter per second squared. However, at the ball's velocity in the y direction at the top of its trajectory for that split second will indeed be 0. But a lot of students make that mistake and think that it's the acceleration is 0 as well there. It's a common mistake, so don't get caught in that trap, please. Example 2.8 is going to, at what time after the ball is being released has the ball in example 2.7 fallen 5 meters below the roof rail? And the title of this problem is 2 solutions or 1. And this is because it's going to, we're going to have to use the quadratic formula to solve this one. So it's going to give us a position, and we're going to have to solve for time. So it wants to know at what time after the ball was thrown is at 5 meters below the roof railing. And so that final position is 5 meters below the roof railing, and we're going to call that -5, right? -5 meters. Our roof railing was here at 0, and now we're here at -5. Remember, we've given this above here to be the positive direction and below that roof to be the negative. So we're going to set up our equation to solve for time using our displacement polynomial. X final equals X initial plus V naught T plus 1/2 AT squared. And if you're confused about this, please refer to my projectile problem videos on YouTube or on your Canvas page. This will go into great detail about this scenario. Okay, so let's go ahead and solve this. So we've got our final position is -5.0 meters equals our initial position is 0. Our initial velocity was 15 meters per second times t plus a 1/2 times -9.8 meters per second squared times t squared. I'm going to add 5 meters to both sides and rearrange this equation to give me a -4.9 meters per second squared times t squared plus 15 meters times t plus 5 meters, 5.0 meters equals 0. And this, you guys, if you can recognize this, this is a polynomial with our variable being t. So this is our constant A, and this is our constant B, and this is our constant C. And we're going to go ahead and use our quadratic formula to solve this, which is t or x, but we'll call it t, equals -b plus or minus the square root of 4ac I'm sorry, -b plus or minus b squared, the square root of b squared. Oh, clear, 1 second. Plus or minus, sorry. B squared minus 4ac all over 2a. All right, so we're going to use these constants and solve for the quadratic formula. Let's see. This calculator doesn't do it. I don't have a poly solver on here, but I will erase all these. And we will get -15 plus or minus the square root of 15 squared minus 4 times a -4.9 times 5 over -2 times -4.9. And then we're going to get 2 answers for t. Let's see, we get t equals -0.3 seconds, -0.3 seconds, and we get a 3.36 seconds. And we're going to go with this 3.3 seconds because we know that time is not going to be running backward in this ever. Time won't be ever running backward. Okay, so you go with the one that makes the most sense. Once again, this is how to solve for time, given position, velocity, and acceleration. Finally, example 2.9 is going to have a solve for velocity given a varying acceleration. And the problem states, Sally is driving along a straight highway in her 1965 Mustang. Sally is cool. At t equals 0, when she's moving moving 10 meters per second in the positive x direction, she passes a signpost at x equals 50 meters. Her x acceleration as a function of time is a sub x equals 2 meters per second squared minus a 0.10 meters per second cubed times t. All right, A, we are asked to find her x velocity and position x as a function of time, and B, what when her x velocity is greatest, and C, what is the maximum x velocity, and D, where is the car when it reaches the maximum x velocity? All right, if you watch my solving for velocity using integration in your chapter 2 instructional videos, you'll realize that the integral of the acceleration is going to give you the change in velocity. In section A, we are asked to find the velocity and position as a function of time. So we know that the integral of that acceleration is going to give us the change in velocity during that time period. So we have from 0 to 2. We put our initial velocity here, 10 meters per second, and then we take the integral of our expression for acceleration, and we get an expression for velocity to be 10 meters per second plus 2 meters per second times t minus 1/2 times 0.1 meter per second cubed times t squared. Similarly to taking the change in the integral of the change in the acceleration function to give us, the integral of the acceleration function to give us that change in velocity, we can take the integral of that velocity function to give us the position, the change in position. So we start off with our initial position, 50 meters, and taking the integral of this expression, the velocity function, we get 50 meters plus the integral from 0 to t of 10 meters plus 2.0 meters per second t minus 1/2 times 0.10 meters per second cubed times t squared dt. And I get an expression for my position to be 50 meters plus 10 meters per second t plus 1/2 times 20 meters per second squared t squared minus 1/6 times 0.10 meters per second cubed times t cubed. Part B asks us to find the maximum value for Vx, and this occurs when the velocity stops increasing, reaches a maximum, and begins to decrease. So this is when dv dt equals a equals 0. So we set our expression up to 0, and we solve, and we get t equals 20 seconds. If I want to know the value of that velocity at 20 seconds, I want to know the value, that maximum value, I'll use that velocity function that we derived, which was 10 meters per second plus 2 meters per second squared times t minus 1/2 times 0.10 meters per second cubed times, that was t squared, using my value that I obtained for t equals 20 seconds. And let's see, I'm going to get 30 meters per second. V max equals 30 meters per second. Finally, to find the car's position at that time, or at that maximum velocity, I'm going to use the position function that we derived, which was 50 meters plus 10 meters per second times t plus 1/2 times 2.0 meters per second squared times t squared minus 1/6 times 0.10 meter per second cubed times t cubed. Once again, I'm going to use my value of t equals 20 seconds, and I will get 517 meters at that velocity when the velocity is the maximum.